Bismillahirrahmanirrahim. Assalamu alaikum. Uh, the topic of today's lecture is the signal flow graph. Basically, signal flow graph is the alternate method to block diagram. Block diagram is also used for the reduction of complex system into a single transfer function or a single block. Similarly, signal flow graph is used to simplify a transfer function into a single transfer function. The difference between the two is that unlike block diagram which has blocks, signals, summing junction, pick-off points, the signal flow graph is simple technique. It has only two components. One is branch. So basically branch represents the system and the node represents the signal. Let's start the topic. The basic of signal flow graph, as I have told you earlier that signal is represented by a node. Whenever there is any signal in our system, we will represent that signal by a node, and system is represented by an arrow. This is the gain of the system or transfer function of the system, g of s. Whenever we draw a signal flow graph, we will replace all the gains or transfer function of the system by a branch. Okay, let's we take an example. Here, these nodes, as I told you earlier, these nodes R1, this is the signal, this is another signal R2, this is signal R3, and all the signals are coming at V of S, and between these two nodes or these two signals, there are the branches, and branches represent the system. This is the G1, the gain of the system 1, or minus G2, gain of the system 2, and gain of the 3. And from this node again, it emerges three further systems, and these represent the gains of these systems, and here comes the signals. Okay, now we will write the output of this C1 of S, C2 of S, and C3 of S. Basically R1 and R2 and R3 are the inputs of the system, and C1, C2 and C3 are the output of this system. So we will write the equations of this. As I told you, these are the signals. These are the input signals, and these are the output signals, and these are the system gains or transfer function of the subsystem, or the gain of the subsystem, or whatever you like to say, you can say it. Okay, example, we will solve, or we write the output at C1, C2 and C3. Okay, what will be the value of of V of S? It will be input multiplied with the gain of the system, R1 into G1 of S, and here it will be R2 into minus G2 of S, and it will be R3 into G3 of S, and this will be the value of V of S. What will be the C1 of S? C1 of S will be equal to the V of S into G4 of S, and we will put the value of V of S, and it will be multiplied by G4 of S, and we will get the C1 of S. Similarly, for C2 of S, C2 of S will be equal to G5 of S into V of S. So we will multiply G5 of S with this V of S. Similarly, we will get C3 of S. You can see the equations of C3, C2 and C1. As I told you earlier, the value of C3 of S will be equal to the minus G6 of S into V of S, and we will put the value of V of S as we have written here, and we will get the C of S. Similarly, we can write the value of C2 of 1 or C2 of S. Okay, now here comes, if there is a block diagram, how can we convert blocks to the signal flow graph? This is we will study. We will uh, draw three types of block diagram, as we have studied earlier that for block diagram there will be three cases. One will be either the blocks or subsystems will be in cascaded or series form, or these will be in parallel form, or it can be in the in feedback form. So here comes the first case, in which we have to convert this cascaded block into a signal flow graph. As we know that when there is a signal, R of S or any signal, we will represent it by a node. So here comes R of S. We will draw one node, second node, third node, and fourth node. Yeah, here comes. We set it X2 of S or P of S. R of S will be presented with the node 1, X2 of S, the output of the first subsystem, or will be B2 of S. Output of this will be B1 of S, and output of the system will be the C of S. Now we will join these nodes by a straight line. This will be called as known as branch, and the direction of flow of signal will be presented by an arrow on the branch. So R1 will be connected with the V2 of S, and we will draw a line here, a branch here, and the arrow represents the flow of the signal, and the gain of the signal will be G1 of S. Yeah, this will be more clear from this diagram. R1 of S is the input signal, V2 of S is the output of the first block, and G1 is the gain of the first. Similarly, G2 with the second, G2 represent the second system, and G3 the third system, and here is the C of S. So this is how we can convert a block diagram of a cascaded block diagram into a signal flow graph. So the second case will be the parallel blocks. If we have parallel blocks, how can we convert these parallel blocks in a signal flow graph? So we will use the same concept as we have used earlier, that we will draw a node for each signal. Here comes this signal, these three signals, x1, x2, and x3. These three signals will be combined, added at this summing junction, then one more signal, and we will get x of C of S. Here comes the draw nodes of the all signals. The same concept we have used earlier for the series blocks. This is the R of S, then the V1 of S, V2 of S, V3 of S, and here comes this signal or signal at the output C of S. Now we will draw the system with the straight line or branch. So with R of S, here come a branch G1 of S, and this will be added at the C of S, and the gain of this branch will be 1. Similarly, here comes R of S into G2 of S, and this will be the V2 of S or X2 of S, and it will be added at this node, and the gain of this branch will be the 1. Similarly, we will draw the branch for the third parallel branch. Clear? This is how we represent the parallel blocks into the signal flow graph. Now we will study the last option or the last model of the block, which is the feedback block. Here we have a feedback block. We will convert this feedback block into the signal flow graph. Here is the input signal, E of S is another signal, C of S is the third signal. So we will draw the three nodes. One will be the R of S, other node will be the E of S, and the last node will be the C of S. Now we will interconnect these nodes and by a branch, and the direction of the flow of the signal will represent by the direction of the arrow, and these nodes will be interconnected by putting the gains of the branch. Yes, these are the nodes R of S, E of S, C of S. These nodes represent the signals, and now we will draw it complete. R of S will connect with the E of S, and the gain of the branch is 1. Here it's come from C of S to E of S, and another branch, and the gain of the system is H of S minus H of S, and the E of S and C of S, these are connected with this plant and controller, and the gain of this system is G of S. So we represent this feedback signal flow graph into the block diagram to the signal flow graph. Now we will solve an example so that the concept of signal flow graph will be more clear to you. It's a little complicated complex circuit, and we have to draw this block diagram to signal flow graph. We have to convert this block diagram to a signal flow graph. So using the same concept as I have told you earlier, we will draw the nodes whenever there is a signal. So how many signals are there? You can R of S, V1 of S, V2 of S, V3 of S, V4, V5, V8, V7, V6 and C of S. So we will place a node whenever there is a signal, and we will interconnect these nodes by the system, and we will write the system gain on the branch, and the arrow, as I told you earlier, arrow represent the direction of flow of the signal. So in the next diagram we replace all these signals with their nodes, as I have told you earlier, R of S, V1 of S, V2 of S, 3, 4, 5, 6, C of S. Now it's a time to connect these nodes by using the branches, or these branches represent the system, and the direction of signal flow will be represented by an arrow. So here is a complete signal flow graph of this block diagram. Let me explain it. R of S will connect it with V1 of S with gain 1. So this, and V1 of S is connected with the V2 of S with the system gain G1 of S. And V2 of S is connected with the V3 of S with system gain 1. V3 of S is connected with the V4 of S with system gain G2 of S, and V4 of S is connected with the V5 of S with gain 1, and V5 of S is connected with the C of S with gain 3. First of all, I have explained you the forward branch gain or forward path. Now we will check the feedback path or feed forward path. Now here comes the branch from V3, and it is connected at V5 with the gain 1. So here comes the V3 and connected with the V5 with gain 1. Again the last output C of S is connected with the V5 of S, and the gain of the branch is H of S. So we connect C of S with the V5 of S, and the gain of the branch is here it comes H3 of S, and here comes V8 of S, and V8 of S is connected with the V5 of S, and the gain is -1. So we draw it as -1. Now V4 of S is connected with the V3 of S via V7 of S. The gain of the V4 and V7 is H2 of H2, and the gain of between the V7 and V3 is -1. So we draw in the same manner, and the last feedback path is from V4 to V1. Here comes V4 and it's V1, and these are connected through the signal V6. The gain between V4 and V6, or the system gain, is h1 of s, and the system gain or system between v6 and v1 of is -1. So we draw the same branch, and we represented all the directions of the signal flow. We have written all the gains of the system, and we represent these signal flow graph into the this block diagram to the signal flow graph. So the concept is more clear to you. Uh, this is the same signal flow graph. We have simplified it further. The branch here again is the one we remove that branch. For example, this branch is connected C of s and V5 of s, and the gate between V8 of s is and V5 of is -1. So we multiplied H3 of s with -1, and we remove the node V8 of s. Similarly, we remove the node V7 of s and connected V4 of s directly with the V3 of s, and multiply H2 of s with minus sign or negative sign. Similarly, the gain or the feedback path from V4 to V7 is connected through the V6 of s, and the gain between V7 and V1 is -1. So we remove this branch and multiply the -1 with h1 of s, and we write it minus h1 of s. So we directly connected V4 of s and V1 of s. So this is the simplified version of this signal flow graph. Earlier we draw this signal flow graph by representing each signal by replacing each signal by their node and each system with their branch. Then once we draw the signal flow graph, then we simplify it in this form. Now it's for your practice. You have to convert the following block diagram to the signal flow graph. We use the same concept. Whenever there is a signal, we will represent it with node, and when there is a system, we represent it with the branch. So you can write the output of each. This is R of s. You can write here x1 of s, x2 of s, 3 of s, 4, 5, x6, x7, x8, x9, and for each signal you will draw the nodes, and then you will convert all these signals by the branches, and you will write the loop gain of the system on the top of the branch, and you will show the direction of signal by putting the arrow. Either it will be from input to output side or output to the input side. It's very simple. You will practice it, and you will get the concept. So before solving any signal flow graph, you should be familiar with the basic definitions of the signal flow graph. First of all, the definition is the loop gain. How can you define a loop gain? Basically, loop gain is the product of branch gain found by traversing a path that starts at a node and at the same node. Means, let me show this signal flow graph. This is the loop. How can you say it's a loop? Loop is the branch which start at the same node and end at the same node. This is not the loop, because arrow is for the direction of arrow is not towards that loop. So you can say that this is the loop, that it's starting from the same node and it is ending at the same node. So loop gain will be the product of all the branch gain found by traversing a path that start and a node and end at the same node. Okay. Now, so here is the loop gains of this. Loop 1 is G2H1. What is G2? G2H1. This is one loop. It's starting from the same node and ending at the same node. And what will be the loop 2? Loop 2 will be the H2, G2H2. G4H2, sorry, G4, this is loop and ending at the same node. Loop 3 is G4, G5H3, G4, G5 and H3, G4, G5 and H3. It is also starting and ending at the same node. Similarly, loop 4 is the G4, G6, H3, G4, G6 and H3. So the product of branch gain, this will be equal to the loop gain. So the second term that you should familiar is the forward path gain. How can you define a forward path gain? The forward path gain, the product of gain found by transversing the path from input node to the output node of the signal flow graph in the direction of the signal flow. Forward path gain means you start from the input node and you have to reach at the output node. You can follow any path, but you should be ended at the output node. So this is the forward path that start from the input and end at the output. So the product of gain found by the transversing a path from the input node to the output node of the signal flow graph in the direction of signal flow. In this case, we have two forward paths. Starting from R1, then V3, V4, V3, V2, V1 and C of S. Another will be this path. So there will be two forward path gain. One will be the G1, G2, G3, G4, G5, G7, and other forward path gain will be the G1, G2, G3, G5, G6 and G7. So as I told you, these are the two forward path gain. Okay. Now next term is the non-touching loop. Non-touching loop, how can we define a non-touching loop? Non-touching loop means the loop that don't have any node in common. Means, as we have seen that here are four loops, loop 1, 2, 3, 4. If any loop has any node common, that will not be non-touching loop. In this case, G2H1 is non-touching with H2 and G4 and H2, but these loop 3 and loop 4 are not the non-touching node because they have the common nodes G4, G5 and H3, G4, G6 and H3. So they have common nodes. If any loop, any two loops or three loops, we don't have any common node, that are the non-touching loop. So the non-touching loop is circled in green and blue. These two are the non-touching loops, and these the red circles. It has two loops, but these are not the non-touching loops because they have the common nodes. So loop 1, loop 2, loop 3 and loop 4. Loop 2 and loop 1 and 2 are the non-touching loops, while loop 3 and 4 are not the non-touching loops. So non-touching loops are the loop 1 and 2 because both loops have no common node. Similarly, loop 1 and loop 3 are also the non-touching loop because both loops have no common node, and similarly loop 1 and loop 4 are the non-touching loop. It's to have no common node. So non-touching loop gain means as we have three non-touching loop. Non-touching loop gain means, as it's very clear from the statement, that non-touching loop, the product of loop gain from non-touching loop statement 2, 3, 4 or more at a time means and these are the non-touching loop 3. If we multiply the loop gains of 1 and 2, we have taken two non-touching loop at a time, that will be non-touching loop gain. If we want to take three at a time, then the product of loop 1, loop 2 and loop 3 gains will be the gain of the non-touching loop. And if we take four non-touching loop at a time, we will take 1, 2, 3 and 4 at a time. That will be the non-touching loop gain. So non-touching loop gain are the, as I told you, product of loop gains from non-touching loops taken 2, 3, 4 or more, depend upon how many non-touching loops are bearing unit system. So by taking the product of the non-touching loop, we will get non-touching loop gain. So these are the basics of the signal flow graph. Now we will, in the next lecture, we will study how to find a simple transfer function from a signal flow graph by using Mason rule. So for in practice, you have to solve the skill assessments and problems of the signal flow graph, and in case of any issue and query, you can ask me in comment section, or we can discuss in upcoming online sessions or in the class. Okay, take care of yourself. See you in the next lecture and after this.